In this video, we start a major class of reactions for this semester, addition to carbonyls. We will approach this topic by functional group, but your learning will be made easier if you can recognize the similarities in reaction mechanism for all types of carbonyls. So by the end of today's lecture, you should be able to say, I can name aldehydes and ketones in the IUPAC naming systems, explain the structural basis for changes in physical properties relative to molecules with similar molecular weight, draw an aldehyde or ketone given its common name, draw the mechanism for reactions between aldehydes and ketones and various nucleophiles. IUPAC nomenclature is just a continuation of work you've already been doing on this topic starting in Orgo 1. So you'll need to just add the aldehyde naming stuff to your knowledge of that, and you can look on the Notes from Orgo 1 Winter 2015 folder on Top Hat, and you'll see a link in there called Nomenclature, an overall handout, and some chapters. So that's where you want to go to do that nomenclature. Here I'm just going to show you some of the common names that you're going to need to know to understand what I'm saying in class. So here on the left we have formaldehyde. This is the simplest carbonyl compound with both substituents being hydrogen. When we change one of those substituents to a methyl group, then we have acetaldehyde. You probably didn't realize that you're already familiar with this prefix acet from acetone and acetic acid. In acetone, the carbonyl takes the ending -one, and then the acet is describing these methyl groups attached to a carbonyl. Then in acetic acid, again, the methyl group that's attached to a carbonyl is getting this prefix acid, and then ic acid refers to the carboxylic acid ending there. Now down here we have acetophenone, methyl ethyl ketone, and methyl vinyl ketone. So here I've highlighted for you where in the structure the names are coming from. So here, again, we have acet for the methyl that's attached to a carbonyl. We have phen for the phenyl group, and we have -one for the ketone. And then here, it's quite literal, methyl ethyl ketone and methyl vinyl ketone. So next we're going to look at the pi bonding of carbonyls by considering a resonance analysis. So first, let's draw an example carbonyl compound. We're going to use acetone, and we're going to include all lone pairs in that Lewis structure. Next, let's look at the resonance structure of acetone to see whether we can predict how it might react. When you're drawing resonance structures, make sure to draw an arrow to move the electrons, then draw the outcome of that movement, which is the next structure. So we get this charge-separated form of acetone. And remember, the structure overall is some mixture of these two pictures. So now we can think about how the molecule might react when treated with an acid. A Bronsted acid, a proton donor, would react at the most basic position. So on acetone, our resonance structures are showing us that we have a negative charge on oxygen. Also, if you look at the charge density map on the bottom left, we can see that the oxygen has the most electron density. So we would expect oxygen to react with proton donors. In many of our reactions, we'll do this step first. Whenever we're treating a carbonyl compound with acid, we'll protonate the lone pair on oxygen, and that'll be a step that we'll call activation of the carbonyl. Just a note for anyone who might go forward in organic chemistry, this is also where a Lewis acid would react, and that can be really important for asymmetric reactions. So what about a nucleophile? Well, a nucleophile donates its electrons to make a new bond, so we need to look for where the carbonyl has a partial positive charge. If we look at the resonance structures, we see that the carbonyl carbon has a positive charge. So we'd expect that nucleophiles are going to add to that carbon. Now we can't just draw this one arrow here because that would make a fifth bond to that carbon. And so next we need to push the electrons up onto the oxygen. When we do this, we end up with 4 sigma bonds to carbon, and we get to an intermediate, which is called the tetrahedral intermediate, because we've changed the hybridization at the carbonyl carbon. We've gone from sp2 to sp3. You can also think about this reaction happening by drawing the resonance structure first. So make sure you draw this arrow to get to this resonance form like we did before, because that arrow will have points that are scored. But it's fine if you want to do that, draw this resonance form, and then draw the nucleophile attacking the carbocation there. So lone pairs on carbonyls participate in hydrogen bonding with H bond donors. Especially in this class, we'll look at water, alcohols, and amines. Since these molecules are significantly less acidic than a typical Bronsted acid, the carbonyl does not fully remove the proton from the H bond donor. The result is a transient or short-term interaction. However, when many molecules are involved, the effect becomes quite significant, as you'll see in the following slides. Another property of carbonyl compounds is that the hydrogens on the carbons adjacent to the carbonyl are more acidic than for a normal alkane. A typical alkane, such as butane shown here, has a pKa of about 50 to 60, whereas the hydrogens next to a carbonyl have a pKa between 20 and 25. So that's a difference in acidity of about 10 to the 30th times. So you can see that the carbonyl has a huge effect, and that's because of that strong delta positive charge on the carbonyl carbon and the inductively withdrawing effect of the electronegative oxygen atom. We call these hydrogens alpha hydrogens because they're at the position next to the carbonyl. So if we're thinking about the carbonyl, the next position is alpha. Over here, this is also alpha. And then here, beta, and then if we had another carbon, it would be gamma, the next one would be delta, then epsilon, and so on. So we use these lowercase Greek letters to refer to how many carbons from the carbonyl carbon our particular position is. So this hydrogen is at the alpha carbon. You can check out this table in the textbook to see the effect of the carbonyl on different boiling points. In this series of examples of molecules with similar molecular weight, there's a huge range of boiling points. The presence of a ketone essentially doubles the boiling point from pentane, which is 36 degrees, to butanol at 76 degrees. And this is because of dipole-dipole interactions that are occurring between molecules. If you're not sure what dipole-dipole interactions are, please see the discussion in Chapter 10, which I've also included on this slide for your convenience. The polarity of the carbonyl also impacts the solubility of aldehydes and ketones. When the hydrocarbon portion of a carbonyl compound is very small, the solubility in water is excellent. However, as the hydrocarbon length increases beyond 3 to 4 carbons, the solubility decreases rapidly due to the hydrophobic effect. The hydrophobic effect is the tendency of hydrophobic groups, like alkyl groups, to self-aggregate and avoid the interaction with water. This is your familiar salad dressing problem. It's impossible to keep the oil and the vinegar mixed together long enough to get even spread of both on your salad. In the next several chapters, we're going to be looking at reactions of either strong or weak nucleophiles with carbonyl compounds, like aldehydes and ketones and carboxylic acid derivatives. For all of these, we will talk about strong nucleophiles versus weak nucleophiles. A good rule of thumb is that nucleophiles whose conjugate acid has a pKa greater than or equal to 15 are typically strong nucleophiles. So in this table, which is a pKa table that I've modified just for this class, you can see the alkanes up here. If you wanted to use a nucleophile that is an alkane anion, you already know you would use butyllithium to get a butyl anion as your nucleophile. For For allyl anion or benzyl anion, you would use the corresponding Grignard reagents. For this vinylic anion, so now the minus is at the sp2 position, not the sp3 position, you would use the corresponding vinylic Grignard reagent. And then for the aromatic ring, you would use phenolithium. That's commercially available. And then for alkynes, we typically use the sodium acetylide. And that's because we generate that directly from the original alkyne by treating with NaNH2, which we'll see later in this video. For positions next to carbonyls, we usually deprotonate those with LDA or potassium tert-butoxide. We'll be covering that in more detail in chapter 19. And then if you want to use an alkoxide as your nucleophile, typically you would start with either the sodium, potassium, or lithium alkoxide, often in a solution of the alcohol. And then finally, for hydroxide as a nucleophile, you can use NaOH, KOH, or lithium hydroxide. Often that depends on the solubility in the solvent you're going to use. So on this slide, we're going to talk about the mechanism for addition to a carbonyl when the pKa of the conjugate acid of our nucleophile is greater than or equal to 15, which is just the long way of saying when we have a strong nucleophile. So we'll do this with a simple example. Here I've got benzaldehyde, and then we're going to treat with sodium methoxide in methanol. So we're going to use the methoxide anion as our nucleophile. I'm showing the nucleophile coming in from in between the substituents on the carbonyl, and that's because in reality, nucleophiles attack in this way at an angle called the Bürgi-Dunitz angle. So the result of that set of reaction arrows is this intermediate here. And you'll note that our carbon where we did the reaction went from being an sp2 center here to an sp3 center here. Remember, sp3 centers are tetrahedral, and so we refer to these intermediates as the tetrahedral intermediate. This intermediate is really important. This is a discrete intermediate that occurs and can be detected in a reaction. And so you cannot ever skip drawing this intermediate in your mechanism. So a lot of times you'll see people take shortcuts where they push the electrons up onto oxygen and back down and do crazy stuff all in one step. We're always, when we react with any carbonyl containing compound where we're doing nucleophilic attack, we're always going to draw this tetrahedral intermediate. So in our next step, we're going to go ahead and protonate. So the result of this reaction is something called an hemiacetal, and we'll talk more about acetals and hemiacetals in the next video. But all the strong nucleophiles are going to react by this type of mechanism. So I'll do one more example, and then I'll leave you with a set of aldehydes and ketones and a set of nucleophiles, and you can mix and match those to your heart's content to practice these mechanisms. So here we're going to treat a ketone, in this case cyclohexanone, with potassium cyanide. You want to be careful if you ever need to actually do this, because cyanide is of course readily protonated, and HCN is both a gas and highly toxic. So our cyanide is going to come in and attack at the Bürgi-Dunitz angle. We're going to push our electrons up onto our oxygen to avoid forming a carbon with 5 bonds. And that's going to lead us to our tetrahedral intermediate. Our next step then is to protonate the tetrahedral intermediate, and that'll form a cyanohydrin. So as I said before, go ahead and take some of these nucleophiles and add them to these electrophiles, and you can practice using a reaction mechanism to predict the product.